Can you speak up a bit? I think your voice went a bit low.
I can't hear you. Can you see the screen?
Sir, your voice is low. It's hard to hear you.
There's no response from the side. Do I assume there's a problem again, or is it just that nobody has responded?
We can hear you, but at least for me, the voice is low.
But I can't hear it.
For Bevin as well.
It means at the moment I switch. Okay, so then maybe I'll just do a monologue right, just in the interest of finishing things. You can always just type the questions here. So you're able to see the screen that our point has shared. Can you confirm the PowerPoint that you're able to see? You can see, and you see it as an open window, right? Not a full screen, right? I think that's okay. So remember, we have discussed the following questions in the past few classes, which concerns, in the context of collective behavior. We discussed various models, right? And along the process, we can ask the following question, right? We did ask this question at some point of time. How do real organisms really interact? And this is a very general question. It's not a question just in the context of collective movement, which you have discussed, but in the context of any sort of biological question. What is the sort of nature of interaction? It could be between molecules, pathways, or could be at a higher level, like organismal level. Okay. Now, and I also discussed a couple of papers in the direction. How people did experiments with just a few fish. Right, and then one, two, three sort of fish, and then third. And there are many ways of doing it. And I showed you one such paper. And then there is also another way of achieving the same result, where, like in the case example of starling frogs, by looking at some macroscopic quantities, they were trying to infer the local interaction. Okay, there are many ways of doing it. Okay. So we I will continue to ask the questions in that direction probably now. Okay. And one thing to keep in mind is when you ask questions like how do organisms interact, it depends on the scale that you are looking at, and also that's the context that you are interested in. Okay. For example, if the question is what keeps groups cohesive, the kind of interaction that you will be looking at will be different. And what if the question is what makes group motion polarized? Again, the answer will be different. And also it might depend on the context, ecological context of predation, foraging. And these interactions can be ecological context dependent. So it really depends on the context that you are looking at. And what I'm going to show you is the work from our one of the few of the former skills of that. The focus will be on understanding dynamics of group polarization. And what is interesting is that to be able to understand this work, I have sort of covered almost everything you needed to in the class. Okay? And so hopefully you will appreciate this better by this. Okay. So the focus will be on the not group cohesion, but group polarization in the context of collective movement. And the focus will be therefore on deciphering the rules of direction alignment. Okay, not be about attraction, but cohesion. It could be about alignment. And in the previous few classes we have studied demographic mass, right? So what I'm going to show is that using the ideas of demographic mass, one can actually say something about how animals interact. Okay, so that's the way. That's the plan for today's class. The next half an hour. Okay, so let me first show you the experimental part of it. The experiments are actually fairly simple. You can see there's a fish tank, almost like a flat fish tank with a very small depth, but a large diameter. And what that ensures is that you can ignore the third dimensional motion of fish schools, and we can do a video recording and therefore record how the fish are moving. And once we have the recording, we can use ideas of image object detection and image tracking from the computer vision literature, and then from that you can sort of analyze how the fish are moving. Okay, let me show you some videos. Please, somebody please confirm me by chat. You can see the videos. You're saying my voice is unclear. Is it too bad? Are you able to see the video now? Thank you. Okay. So we also some video of fish moving, and with that, what we can do is, analyze sort of, Okay. So what we can do is we can construct trajectories of fish, how fish are moving. What does it really mean? What it basically means is that, see, every fish has some location, x and y coordinate at some time t, and that is changing over time. So x and y for each fish I is changing over time. So using these basic principles of computer vision, you can actually construct what is this x and y for each fish as a function of time. Of course, when you begin to implement that, you will realize that there are lots of challenges in doing so, because when two fish cross trajectories, basically almost no algorithm can figure out who went where. Okay, so it's very difficult to maintain identities for a long enough time, even when the best methods are available in the computer vision. It doesn't matter what methods you get, AI and then whatever you like, even then the best methods don't work very well under these kind of even simple experimental conditions. Okay, so we have this, from this what we can do is we can construct the parameter, the following parameter called group polarization. So what is this? So this group polarization is basically a parameter where you take the orientation vector of each fish. So I represents the fish index. 1 to n means, for example, in the previous video, I think there were 30 fish, so n will be 30. So you take the direction of each fish and you do a vectorial addition of those, all the orientation, and then you divide that by n. So then you get something called group polarization. It's a two-dimensional vector. So what is this? So you take the modulus of this vector m. If the fish are all randomly moving, if they don't have directionality, this modulus will be close to 0. On the other hand, if the modulus of this m is close to 1, then that means that fish are all sort of aligned with one another. Okay? That means m is equal to 1 means they are highly polarized, m is equal to 0 means they are disordered. Okay, now we look at, let us now plot this modulus of m as a function of time, and this is how it looks like. So for we have, there are different experiments of different group sizes. When there were 15 fish, this modulus sort of fluctuates and all, but they also hit the maximum value of 1 frequently enough. But when you are at a larger group size, you can see that you rarely hit the maximum value. Okay, so they are in general not able to hit large values of polarization. So, and these experiments run for 1 hour roughly for each of these cases. So here is the question. What we have now done is we have quantified a group property, which is group polarization. So we can then ask, how can I infer something about individuals by looking at group level data? And also remember, these data look very noisy, rather very stochastic. There is nothing very stable or fixed about this. So for example, if you were to think of deterministic models of collective behavior, for example, if you think of the binary choice model or the ternary choice model, If you look at the deterministic mean field approximation, they just predict that this order or disorder, right? Depending on the parameter values. But in that means that they have a high value and that's a constant value. But what you are seeing is that if we take such a deterministic model and add some noise, it's not a satisfactory explanation because things are so much dramatically changing here, right? Compared to what a deterministic model with some noise will do. There is a lot of fluctuations that we must be able to understand. So that's where comes the idea that you can actually use stochasticity to infer something about the model or the individual rules that are going to follow. Okay, let me just now this theory is something that you already know. I have already covered. Before we do that, let me show you these interesting graphs. So by the way, so there are now two graphs here. Okay, so in both of them, I am plotting polarization as a function of time steps. Okay, now as you can see, these values are ranging from -1 to +1. So let me tell you something very interesting. These actually come from the model. They don't come from real data. They actually come from model. I'll tell you what that model is very soon. So as you can see, let us observe these dynamics. So you can see that the polarization is going all the way up, it's coming down, it's going up and down, it's sort of fluctuating a lot. And same thing is happening here. It's again fluctuating a lot, going up and down. Okay. And let us plot the PDF or the histogram from the data. Okay. So if you plot the histogram from this data, what you find is this M has a maximum at close to -1 and again at 1. And something very similar even for the plot B. Both plot A and plot B, the sort of PDF or histogram are qualitatively similar. Of course, there are quantitative differences, which is fine. Right? If you change parameter value, there will be changes quantitatively as well. Okay, so this is the data. This is the histogram of the data. Okay, let me tell you something very interesting. So these two time series I just showed you, they actually come from different models. And these two come from models we have actually studied in the course over the last few weeks. Remember that I described something called a pairwise interaction binary choice model. And we also described something called ternary interaction binary choice model, right? I won't repeat those again. I'll just summarize those in the next slides. But what is interesting is that although they come from two different models, the time series looks very similar to our eyes. And if you look at this histogram, they actually look very similar to our eyes. Okay, now, again, remember that in those models of binary choice, the parameter M could go from -1 to 1. -1 meant that they were all going in one direction, let's say left direction. +1 meant that they were all going in the right direction. Okay, so of course, this model is done in one dimension, and although the data that I initially showed you come from 2 dimensions, I'm showing this for representative purposes because 1D results are easy to understand. Okay, so in fact, I had actually asked this question on one of the lab assignments. I think the lab assignment 2 weeks back. Okay, so where I asked you to derive mean field model of ternary interaction, and I had asked you this question in the end. If somebody gave you data of fish schools, can you distinguish whether it came from pairwise interactions or ternary interactions? I had asked you this question. Okay, I think the predominant answer was as follows. Pairwise interaction model says that there will be no order, whereas ternary interaction model says there will be order. Therefore, if you see that the fish school is showing order, it must come from ternary interactions. Whereas if the results show disorder, it comes from pairwise interaction. That was the answer given, which is a reasonable answer. Okay, because it's a reasonable answer in the limit of deterministic mean field approximation. Okay, so what's the limit in which deterministic mean field approximation is valid?
The population should be large enough.
It's about that answer. What's the limit in which deterministic mean field approximation is valid? Concepts?
Margin of mean field.
Okay, I have a question. For larger, excellent. It's large number of images. I have three answers. Excellent. Yes. When n is really large, that's absolutely right. In that case, you don't expect order from pairwise interactions. You expect order only in the ternary interactions. But what I have done here, but what about the fish schools we studied? They were all done for small sizes, 15, 30, 60. They were not like thousands and millions where mean field approximation becomes a valid approximation, right? Okay, so therefore, when we are dealing with real data, we have to account for stochasticity as well. Okay, and I showed you how in the class, how even with pairwise interactions, when you have large stochasticity, which corresponds to small n, which corresponds to small n, you will actually get order even in pairwise interaction, right? So in fact, that is precisely what has happened here. These are basically simulation data for small, school size, small population size. In such a case, it is possible to have order even with this pairwise interactions. Okay? Let me just remind you what is pairwise interaction. It's possible to generalize the pairwise interaction model to two dimensions also. For example, if there are two fish moving in direction θ1, θ2, at some rate c, the second fish will copy the direction of the other fish. Okay, and of course there is a stochastic turning. So in the case of 1D, it would be 90-degree turn. In the case of 2D, the turn can be need not be a 90-degree turn. Sorry, need not be a 180-degree turn. It could be any, it could be actually a continuous turn. So this is the pairwise interaction model in two dimensions. And what one can now do is, the ternary interaction as well, where again have three fish moving in slightly different direction. The way the ternary interaction works now is the individual who is in a minority. So in this three fish, so this guy is sort of off compared to these two. So I'm defining minority in the following sense: the one who is most deviated from the rest of the group. So in this, it's visually clear that it is this individual who is slightly away from the other two. So this individual will turn towards one of the two individuals here. This is called ternary interaction. Okay, now you remember in the last class, in the last lab, I think I asked you to actually derive the demographic noise, or what we call the noise part for the ternary interaction model in 1D case. And I myself showed you how to do this for the pairwise interaction. So it's possible to do this for 2D as well, except that the algebra is incredibly more hard. Okay. So, but what is interesting is that if you take the 2D continuous model with pairwise interactions, you actually get a very similar equation. dm by dt, where m is the order parameter, is minus am, that's the deterministic term. Okay. Where m is now a vector, it's not a scalar anymore, it's actually a vector now, plus a square root of a plus c to 1 minus m squared. Where what is a? A is the spontaneous term. A is basically related with spontaneous term. Okay, I won't define epsilon here, it's a bit trickier term. I need to, I have simplified a bit here. Okay, and then so it actually has the exact multiplicative noise structure that we did in the 1D case with a slightly redefined parameter for the stochastic term. The stochastic term. Instead of this, we now have A. Okay, and you can do the same for ternary interaction model as well. You will find the deterministic part is exactly the same with the scalar m replaced by a vector m. Okay, and again, the noise part, okay, again has the exact same feature. It has 1 minus mod m squared term, and some coefficients change, and that could just be a consequence of rescaling. It doesn't mean something substantial. Again, it has a multiplicative noise. Okay, so what you see is that whatever we learned broadly in the 1D case also nicely translates to 2D case. So Sharaj has a question: what order of magnitude of population is usually considered as a loss population? So let's think about this term, right? If this term is of the order of, let us say, let's say A and H are two coefficients. if this term is has the same magnitude, then you can say they're comparable, right? So that would mean that n is that would trivially mean n is close to 1, but that would be too very constrained. But maybe one can say that if it is at least one order of magnitude, right, more, one order of magnitude as strong, then you can say n is 100 is anything less than 100 will be a small population. But usually because you have a square root and a noise term actually decays slower than deterministic term, right? Noise term is square root of dt sort of dt, right? Convergence, right? So therefore, usually we take at least 1000 as a population size for you to think of it as a large population size. But I think 10,000 would be even better. Usually, 10,000 is when you can sort of begin to ignore these terms, 10,000 individuals. I think anything smaller, it's useful to keep in mind that it may have a significant impact. For it to have an actual impact in terms of changing the phase, the bifurcation diagram itself, you may often have to come down to much smaller numbers like that. Okay. For example, in the discussion on pairwise interactions, we discussed how there's a critical value of sigma, beyond which you will have different noise-induced states, right? To sort of reach those, you may have to have n of order of 100, but that will depend on the values. Okay. So anyway, so what this shows is that if you look at what we call mesoscopic models, these are all called mesoscopic models because they are not macroscopic mean field in the sense that n is very, very large, therefore stochastic can be controlled, but they're also not microscopic. Microscopic are the rules that I described about. These are the microscopic models. So, but macroscopic model would be just this, what we have in the blue, blue circles. Okay. So it's in between, so they're called mesoscopic models because in these mesoscopic models we also capture stochasticity arising from finite segment systems. So what you see is that the difference between pairwise and ternary models are as follows, right? One is that the deterministic term is actually different. Qualitatively, it's linear, it's cubic here. Unsurprisingly, stochastic term is very similar. They both have 1 minus m squared term, except that here n minus 1 minus m squared term also has a higher order interaction, which is the ternary interaction. So any questions up to this so far? So this slide is basically summary of what you did in the class on Friday, but with 2 dimensions. Okay. So now here is a question you can ask. So now I know from models that if the real fish followed pairwise, this will be the differential equation, stochastic differential equation. If the real fish follow ternary interactions, this will be the stochastic differential equation. Now, one way, in principle, we can address the question of what do fish really do is if I can somehow know what is the differential equation for the fish. Is that even possible? Okay. So in fact, it turns out it actually indeed is possible. So here is an interesting thing, right? Although the time series for M come from 2 different models, they can look very, very similar. Okay. And the histograms or PDF can also look very, very similar. But these 2 terms, the stochastic differential equation terms, can be very different. So surprisingly, luckily, it turns out that it is actually possible to construct the deterministic term, what is also called drift term, and stochastic term is also called a diffusion term from the data itself. Okay, so I will not be able to go into that. How do we do this? If you're interested, I can suggest references. So what this basically shows that if I just gave you this pairwise copying time series data, it's actually possible to construct deterministic term of the STV, and that would be a linear function. On the other hand, if you have ternary interaction data, it's actually possible to construct stochastic differential, the deterministic term, which actually will be a cubic term. Okay, and of course you have to be careful while constructing this. Otherwise, sometimes we get false signals as pairwise. Okay, so basic idea is that you can actually construct model from data. Okay, and what we do in the real data is we apply this technique of constructing this drift and diffusion term also called deterministic and stochastic term, okay, from the data itself and apply to real data. Okay. This is why we call it as noise as signal, because we use the stochastic time series and we sort of filter and use the information as signal to understand something about the real organism. So if you remember that we had these data from real fish, and then what we now do is we construct an equation like this. What is really surprising, this is not an equation from the model. This is actually an equation that we got from data. Okay, and it actually is exactly the same form as the pairwise interaction model. So if you construct the diff term, that will be a linear term. To construct the diffusion term or stochastic term, that will be 1 minus n square term with the square root. And because, and crucially, deterministic term doesn't have a cubic term. Because there is no cubic term, therefore we can put out the fact that there are more ternary interactions. Or at least ternary interaction, even if they are present, they're actually very weak in the data. Okay. So therefore, what we can infer is that because the model derived from data has the same form as the model for the pairwise interaction model, most likely fish are following pairwise stochastic interactions. And what does it also mean? It also means that if the order that you see in the data is entirely because of the fact that n is small, therefore stochasticity is large, and the large stochasticity is driving the system away from n is equal to 0 equilibrium. Okay, and therefore this kind of an order is called a noise-induced order. Does it make sense? Are you seeing my entire screen or only my presentation? Okay. Okay, so this is, so I wanted to just cover this last point in the class today. I'll just stop here. I thought this exercise also had how these functions look like from the data, but I will not have. I'll just show you maybe from the I'll just show this. Okay. So I hope you're able to see this. So you can see that, so this is a deterministic term derived from data. And here, the data nicely fit on a plane, which means that the function is a linear function. On the other hand, if you look at these data, which are for the stochastic term, of course, now it's in 2 dimensions. So it won't be a 1 minus m square, it will be an inverted parabola, right? But with 1 minus m square in 2 dimensions will be a dome. So what you're seeing is 1/4 of a dome shape thing. And in fact, and another thing very interesting is that the analytical prediction is that this dome side, the front of the dome at m is equal to 0, must follow in 1/√n fashion. Okay, and that's precisely what we find here. Okay, so 3 different group sizes. The blue is 15, the orange is 30, and the green is 60. This dome-shaped one is changing with n, and again, remarkably, just as analytical theory predicts, if it is a pairwise interaction, the group size does not influence the deterministic term at all. If you remember, deterministic term was just minus alpha m, right? So minus sm or alpha m, depending on what parameter we use, and that means that there is no n dependence there. And precisely in the data also, there is no n dependence for the deterministic term, but there is root n dependence for the stochastic term. So based on this, what one can conclude is that so there are two interesting things that one can do here. One is that can actually construct model from data, which is really interesting in my opinion. And secondly, if we have a general enough model, we can now begin to distinguish what are the microscopic sort of nature of interactions. For example, pairwise model predicts a linear, some functional form for like stochastic and deterministic terms, whereas higher order models predict some other form. So using those, one can not only construct the model but also infer microscopic rules as well. Any questions on this? There are no questions. I'm sort of I'll stop here. I don't have anything more I wanted to cover for today. As I promised, I will cover. I covered one more empirical example, where what kind of techniques we have learned can be used in real systems. And we will do a final meeting on Friday for the final class. You can ask me any questions or if not, we're done with that class. Thank you.
Hello, am I audible?
Okay, so there are no questions. We can wrap up the class today. Oh, there was some question. Oh, sorry. Well, unfortunately, you're still not audible. Okay. Can you share this? Why is my mic messed up? No idea what's happening. I'll share the reference after this. Anything else? Maybe you should just type the question, because although I have unshared, I still can't hear you guys. Yeah, sure. Go ahead. Please type. You need to type the question for us. In case I'm not seeing this state, how to treat empirical data and design methods. Yeah. So first thing to note is, let's see if we have had, if you're lucky enough to have long enough highly resolved time series data. Okay, say if we have such a data. Now you need absolute data, it makes it very difficult to infer large induced state. Okay. So first of all, you need to have a high resolution long enough time series data. And from that, we can use the diffusion method to derive what is the underlying SDV, underlying stochastic differential equation, right? So now, from that, now you now got an SDV. So if the order parameter for your system is some m, we will be able to write down m dot is equal to f of n plus g of n eta t. Okay, where f and g came from empirical data. Now, this alone cannot tell you anything about the mechanisms. To really understand the mechanism, you need to have a theory. The theory, some reasonable theory that you come out of it, and the theory must using, let's say you have, and when I say theory, what you need is a zoo of models. Say model one. For model one, you have some mechanism one, and then they derive a different stochastic differential equation for it. You have a mechanism 2, again you derive stochastic differential equation for it. So now we have a zoo of mechanisms, and for each mechanism we have a corresponding stochastic differential equation. Now, so now you see which of these models best correspond to the data-driven stochastic differential equation. So data, based on this time series data, you derived the stochastic differential equation, right? So which of your model SDEs correspond to the data-derived SDE? Whenever there is a match, you can say that that's the mechanism that is most likely operating. Now, it is entirely possible that multiple mechanisms produce the same stochastic differential equation, which means you cannot distinguish those different mechanisms from this kind of method that I just described. Does that answer your question?
Yes.
Thank you. Any other questions? So if your group hasn't yet sent me the dates for final presentations, please do tell me.